share the screen so you get the, give you 1 minute. 1 more minute, that is. All right. Locking in 10 seconds. 5, 4, 3, 2, 1. All right, so what do we do? What do we do? Test it, analyze it, whatever language you want to use, that's what we do. Because once we have the model, we want to make sure that it's useful. If you can compare it against observational data, that's awesome. If you don't have observational data, kind of like what we had with the example with the flow in and out of the pond with the chemicals, right? At least analyze the solution to see if it makes sense to what you would expect, your experiences, right? That's another thing that we can judge against. So as long as you gave me anything along those lines, you probably got it 3 out of 3 for today. I'll have to look at them a little bit closer or more closely, but it'll work. All right. So we want to deal with more models. I don't want to be open for the class. Excuse me. You can find if I sit right here. All right, so we want to keep building models, getting models, finding solutions, analyzing. Okay. So, example for today. Oops, I need to actually be with a pen so I can write. We're going to suppose that the population of mice in a specific field is modeled by the following. When I say field, I mean like farm field, not area of study, not academic. So this is modeled by the change of population, which I'm going to use as a capital P, over change in time, is equal to P times 19 minus P all over T plus 1. We're not done with the setup. Researchers in the field spent hours one day looking for mice in the field and only found, write out number, 10. I guess grammatically it would be better if I said researchers spent all day looking in the field. Let me at least try to have it grammar. So based on the model, let's say found 10 on that particular day. many mice would they expect to find 8 days from now? What's up? Okay. So I have my model, i.e. the differential equation. Not only do I have my differential equation, I also have a what? Yeah. Initial condition making an initial value problem total. So the IVP is just time is equal to P times 19 minus P over T plus 1. If I just let 0 represent the day that the researchers were out in the field, my starting time, then I know that there was 10 at the very beginning. So I need to solve this initial value problem. And I look at it. And I say, is this a form that we know how to get the solution to? A couple of you shaking your heads, yes. What type of equation is this? What type of equation is this? Yeah, separable equation. Up in the numerator. I have a function of my solution in the denominator. I have a function of my independent variable. Which means that the solution is going to be the form h of x is it minus g of x equals c, where not h of x, h of y. In this case, it'd be capital P because that is my, I get my variables correct. In the general case, when our solution was y, it was h of y, but here my solution is represented as capital P, so it's h of capital P minus another function of my independent variable, and when we were working with it in general, it was x, here it's t. Where h of p is just the antiderivative of that function of p with respect to p, and g of t is just the antiderivative of my function of t. Ooh, that's going to be confusing the way I wrote it. I'm going to erase that for now. That is how we get the solution. I want to be careful here. If I replace my y with my capital P's, my x with my lowercase t's, this is the type of equation that we're looking for. I needed a function of my solution times its derivative equal to a function of time. Now I do still have that. I still have a function of my population and a function of my time. However, I have to be a little careful here because it's not the way they look immediately. I wanted to prep this differential equation a little bit. So I can see exactly what I need to integrate. I have a p times 19 minus p divided by t plus 1. So I need a function of p being multiplied by my derivative on the left-hand side, which means I need to move those p's from the right-hand side to the left-hand side. So what should I do to both sides? So I need to rewrite this differential equation as a function of capital P, as in Paul, times the derivative of P equal to a function of lowercase t. Oops, both of them came through as mumbles to me. I apologize. Maybe that's why I shouldn't sit in the back of the classroom. But what did you say? Might have been right. I couldn't. You know what we're going to assume? So if I multiply by t plus 1 on both sides, it's not in a bad direction. But what's going to happen is I get t plus 1 times my derivative of p with respect to time. Equal to p times 19 minus p. That's not what I want. I want solution of my independent variable, function of my independent. Oh, gosh darn it. I'm going to go take a sip of my caffeine while I go talk. Apparently I'm off right now. I'm going to blame that discussion I just had with that. It's not my fault at all. I don't need a function of my independent variable here. I need a function of my solution, which means I probably shouldn't be moving the t's. What should I be moving instead? The p's. So I don't want to multiply both sides by t plus 1, but instead I want to do what? I can multiply both sides by p, but that's not going to do anything to this term right here. Yeah, just divide by the p times 19 minus p. Divide both sides by. I'm not necessarily going to get nice, easy. Excuse me again. Let me make sure more space. So right here. So I'm not going to get nice functions necessarily, but I get to set up in the way I want. And now this is set up in that form of a separable differential equation. I know what I need to solve for, and I know what I need to integrate. So what we need is to figure out what is the antiderivative of 1 over p times 19 minus p with respect to p, and antiderivative of 1 over t plus 1 with respect to t. Once I have those two, then I know what my general solution is going to be like. Once I have the general solution, I apply the initial value problem to figure out what the c is. So I have to do both these integrations. We're going to do both of them. Which one looks easier to you? Yeah, the 1 over t plus 1. So note that my g of t, if I'm just kind of matching up with that what we have up there in the top right in green. What is the antiderivative of 1 over t plus 1 going to be? And there's technically an integrating constant c, but we're already accounting for it when we go to our general solution. So in calculus, we get a smack on the wrist for not including it, but in differential equations, we're okay because we're accounting for it later. What about the harder one? 1 over the antiderivative of p times 19 minus p, whoops, with respect to p. What can I do here? Well, if it was just 1 over p, would you be able to integrate that? If it was just 1 over 19 minus p, would I be able to integrate that? Yeah. There's another Calc 2 trick, which I'm going to get to bring up and remind everyone of again. Partial fraction decomposition. Because I can break this up into two fractions where it's going to be easy integration. I just got to figure out how I need to break it up. So I need to figure out how I can rewrite this 1 over p times 19 minus p as something over p plus another something over 19 minus p. Because if I can figure out what a and b are and then break up that fraction, it's going to be two easy integrations. All right, so I need to go about solving what a and b need to be. First step is to multiply by the common denominator. So I multiply everything by this p times 19 minus p. Come on, give me a there we go. There's going to be a 1 is equal to a times 19 minus p plus a b times p. Distribute that 1 or the a through. We're going to get a 19 times an a minus an a times a p plus a b times a p. And remembering a and b here are going to be constants that I need to figure out. I can factor out that common factor of p, as in Paul. And then instead of writing negative a plus b, I'm just going to rewrite that as b minus a. And this right here is all I need to figure out what a and b need to be. So on the left-hand side of this equation, how many p's, as in Paul? How many do I have? None, right? I have 0. On this left-hand side, I really have a 1 plus a 0 times a p, and I need this to be equal to 19 times an a plus b minus a times a p. So if I need to get rid of that p on the right-hand side, b minus a has to be equal to what? 0. And then the only thing that can change that to give me a 1 on the right-hand side is if I set a to be a particular value. Because I need 19 times a to then become a 1. So I get that little system of equations. That first one then tells me that b and a have to be the same thing. And if I want to subtract one from the other and it goes 0, they have to be the same. The second one tells me that a has to be what? 19. And since a is 1 over 19, what else is b? Same thing, 1 over 19. So this means that when I go back to my integration, 1 over p times 19 minus p with respect to p, this is the same thing as the antiderivative of 1 over 19 divided by p by a plus 1 over 19 times 19 minus p. And then I'm going to rewrite these integrals a little bit just to make it a little bit nicer, but hopefully you see where the integrations are going to go. I can always split any integration over an addition, and then I can always pull out a constant multiple. So I have 1 over 19 times the antiderivative of 1 over p with respect to p plus 1 over 19 times the antiderivative of 1 over 19 minus p with respect to p. One of those I hope is easy because we've seen it a couple times now. We're breaking off that dust from Calc 2. One of them, we have to be a little bit more careful. Easier one's the first one. What's the antiderivative of 1 over p with respect to p? Oh, you got this one. What's the antiderivative of 1 over p? Natural log of the absolute value of p. In Calc 2, there's technically a plus a constant. Why do I not need to worry about it in differential equations? Yeah, we're going to add it in later. That second one, I have to be a little bit more careful. What's missing? To make it a nice little, oh, it's the natural log of 19 minus p. If I set u to be what's down there in that denominator, do a u substitution, so that I can make it a nice little simple integration like we do with that first one. I say u is equal to 19 minus p. But if I take the derivative with respect to p, what is the derivative of 19 minus p going to be? Negative 1. Negative 1. Derivative of any constants always? 0. So it'll be the derivative of 19, which is 0, minus the derivative of p, and the derivative of p with respect to p is 1. So it ends up being a negative 1, and I get du is equal to negative dp. So to apply that log integral that we know of, I need the derivative divided by the original function. I don't technically have the derivative because what am I missing? I don't have a negative dp. Positive, right? So I need a negative 1 to appear without changing the formula, which just means all I need to do is multiply by 2 negative 1s. Get this. Negative dp divided by 19 minus p, it's antiderivative. Now that's set up where I have in the bottom the function that's in the denominator, its derivative in the numerator. So when I integrate it, it becomes what? Natural log of 19 minus p. And again, there's technically an integrating constant c there, so we're going to handle it later on because we have included that in our general work. But now I figured out what the two integrals are. Right? When I integrate this 1 over p times 19 minus p, dp over dt equal to 1 over t plus 1. I integrate with respect to both sides. This is going to give me 1 over 19 times the natural log of the absolute value of p minus 1 over 19 natural log of the absolute value of 19 minus p is equal to natural log of the absolute value of t plus 1. All right. My goal is to solve for P. Which means I'm going to need to be rewriting this equation. So I have to think about what can I do here. Well, I've got all these natural logs, and I'll probably want to get rid of the natural logs. So I'd want to raise everything to what? E. But I got to be careful when I do that. Okay? Because if I raise everything on the left-hand side to an E, that means I have to raise that difference to the E. So I won't have just E to just the natural log of a function and then be able to cancel them out. I have to do a little bit more work with that left-hand side. The right-hand side, E and natural log will cancel each other out. Well, let's start rewriting that left-hand side then. Maybe I'll be able to combine those two natural logs that are connected by a minus sign into a single natural log. While I let that sit in your brains for a moment, one thing I'll do is say, hey, here's a common factor of 1/19. Let's pull it out. So you get natural log of the absolute value of P minus natural log of the absolute value of 19 minus P. We use square brackets. So I know exactly that I'm multiplying all of that by 1/19. Natural log of the absolute value of T plus 1. So, whoops, I forgot. What did I forget? I said we'd save it for later. Let's see. Why didn't you catch that before? You could have saved me a headache. You could have been the star people like, ah, I found your mistake. So I just want to make sure everyone sees we're finally bringing in that integrating constant that we said we'd save for later. Because it's still there, and admittedly it could be a bad habit. You save it for later and then just forget, you kind of run into a scenario that I just did. So don't be like me in that sense, but it's okay to be like me in that sense. All right, I need to combine those two natural logs on the left-hand side. There's actually a property of logarithms that deals with the difference of logs. Anyone happen to remember? Yeah, it deals with division. Pre-calculus strikes again. Log of A divided by B is the same thing as log of A minus log of B. It doesn't really matter what your base is, and as long as the B is not 0. This is how you're usually seen it written. But just because we read from left to right doesn't mean equalities only go from left to right. They also go from right to left. So if I have the difference of two logs that have the same base, I can combine them together by log of the first thing. I take the inside of the first one minus log of the second one becomes log of the first thing divided by the second thing. So here I have 1/19 times natural log of the absolute value of P minus the natural log of absolute value of 19 minus P. Which means I can combine them together in this way. All right. It's starting to look a little bit nicer. What else could I do? Do I want to go ahead and raise everything to the E now? Do I want to maybe rewrite it a little bit more? So I got raise to the E and rewrite it. Anyone want to be a breaker? Need a third opinion. Rewrite it. All right. Got a second opinion change to rewrite it. Or rewrite it. Really? Either way, I would have taken the same answer. Great thing about algebra. So what I'm going to do to rewrite this is kind of declutter the left-hand side a little bit, right? My goal is to get a P, so probably the less things I have interacting with a P, the better. So I don't want to have that 1/19 on the left-hand side. Let's move that term, or get rid of that term on the left-hand side by doing what to both sides? Yeah, dividing by 1/19 or equivalent is multiplying by 19. So then I'm just going to get natural log of the absolute value of P over 19 minus P is equal to 19 times the natural log of the absolute value of T plus 1. Plus, I get 19 times a constant, but in differential equations, that's still just a constant. All right, well, 19 is still going to be a little bit pesky, but at least it's away from the P. So now, let's raise everything to the E power. Again, so I can just keep everything on the same line instead of using E and then trying to write a bunch of stuff up in a superscript, i.e. the exponent. Let's just use that EXP notation. It's going to come in handy here. What is one easy consequence of doing this rewriting of the equation? And also why we decided to raise everything to the E power. Yeah, get rid of the natural log on the left-hand side, right? Because on the left-hand side, I do have an E to the natural log of a function. And that's it. The E and the natural log are directly interacting. The left-hand side, I definitely get absolute value of P over absolute value of 19 minus P. What about that right-hand side? I don't get just direct interaction between my E to the whatever and the natural log. Because what else am I doing to that natural log up there? Yeah, multiplying it by 19. So I don't get to take advantage of the same property that we did on the left-hand side just yet. What can I do with that 19? So that I could, in the next line, then take advantage of it. What was that? Go for it, Malcolm. No. What did you say? I can't distribute through that natural log. Natural log's not simple, but there is a natural log property. Yeah, power rule, right? Normally, again, oops, I think I usually do a little more. One of the rules when you're trying to break down logs is if there is an exponent to everything inside the log, I can pull that exponent out front and turn it into multiplication. In this case, I don't want that multiplication out front because it's interfering with me getting rid of the E in the natural log. So let's raise that 19. So I take the absolute value of T plus 1 and raise it to the 19th power. Oops. Plus C, and then technically, I still have one other pesky issue because it's not just a natural log up in that exponent. I'm adding a constant to it. But what was the trick that we do with a constant? So we can essentially say, don't need to worry too much about it. That's not 0. That's a good guess. Yeah, but if y'all got it, e to the constant's a constant, right? Because if I'm adding things in the exponent, it's the same thing as if I multiplied the two things with the same base. Oops. Natural log, that's the value of 2 plus 1 to the 19th power. Now, can I finally cancel out the e's in the natural logs? Absolutely. And e interacting directly with the natural log and its exponent, and the natural log is the only thing in that exponent. So I get the absolute value of p is equal to the absolute value of 19 minus p equal to c times absolute value of t plus 1 to the 19th power. Almost done. Almost done. All right. I still need to figure out just a function of p if I can. So first thing we probably want to do is get rid of absolute values. Usually we don't like to deal with those, so maybe I can make some observations. That's going to help out. Population, p should always be positive. We can never have a negative population. So at least in the numerator, I should have a positive value. In the denominator, I would have a 19 minus p. Is it possible that my population can get above 19 field miles? Yeah, it's possible, right? Which means that the denominator can either be a positive or a negative. But I can account for that by incorporating that positive or negative into what? The constant c. It's a nice little black hole that gets to absorb all these other constants. So I technically have p over the absolute value of 19 minus p equal to some constant times the absolute value of t plus 1. We'll deal with that absolute value here in a second. So I get p is divided by 19 minus p is equal to technically plus or minus constant times absolute value of t plus 1 to the 19th power. C is equal to plus or minus c. We can do this up here. C is equal to e to the c. Then we got one more set of absolute values to deal with. Well, time starts at 0 and only increases. So t plus 1 is always going to be what? Positive or negative? Always going to be positive. So absolute value of positive number doesn't change it. I can rewrite that as u over 19 minus p is equal to some constant times t plus 1. Since t plus 1 should always be positive, never have to deal with a negative number, I can drop the absolute value signs. All right, getting a little better. But I still need to solve for p. Yeah, multiply both sides by the 19 minus p. Let's get everything on the same level, right? Get things out of fractions. So then I get p is equal to 19 minus p times a constant times t plus 1 to the 19th power. And then, hey, if I distribute this c times t plus 1 to the 19th power through, I get a 19 times a constant, which is just going to become a what? Constant. Ooh. I need to be careful here. That was issue right through. So I do have to be careful. because when I distribute this c times t plus 1 to the 19th through, I'm going to get that constant c now show up in two places. I'll admit this is a mistake that I'd like to make. It's tricky. That constant c is a constant value, but it's representing a fixed value. Is 19 times a constant the same thing as that same constant? Said differently, is 19 times c equal to c? Generally, no. Right? Only if it's 0. That's the only case that would ever be true, is if that constant c was 0. But if that constant c was 0, then I wouldn't have anything to deal with. P would be 0. So at this point, I have to be careful because I get that constant showing up in two different places. So I need to make sure I don't change it anymore, which is why I'm going to keep it as a 19 times c. And then I have this, I can move all of my p's to the same side. So this will be a p. What was that? Oh, yeah. Thank you. Yeah, it should be 19 times c times t plus 1 to the 19. So I'll get a p plus a constant times p times t plus 1 to the 19th is equal to 19 times c times t plus 1 to the 19th. And now I'm close to being done because on that left-hand side, they both have a common factor of what? P. I can factor that out. And then divide by that term to get my solution. The function that governs the population based on this model is 19 times a constant times t plus 1 to the 19th power, all divided by 1 plus a constant times t plus 1 to the 19th power. There's not much more I can do to simplify it. I'm going to try to take us through this quickly because we only have a couple minutes left. I have an initial condition. We said on the day that the researchers went in and counted the number of mice, they saw 10 mice. We said we're going to let t be 0 be that time. So we're going to apply that p of 0 is going to be equal to 10 to find out what that constant c needs to be. So I need 10 is equal to 19 times c times 0 plus 1 to the 19th, all divided by 1 plus c times 0 plus 1 to the 19th. Well, 0 plus 1 is 1. Anything to the 1 to any power is always just 1. Meaning that I have 10 is equal to 19 times c plus, or divided by 1 plus c. Well, again, same issue we had before. We have a c in the numerator and denominator. Well, let's get everything on the same level. So multiply everything by 1 plus c. Give me a 10 plus a 10c is equal to a 19c. Subtract 10c from both sides. And then I get that that constant c needs to be what? Over 9. So the solution to the initial value problem is e is equal to 19 times 10 over 9 e plus 1 to the 19th power, all divided by 1 plus 10 over 9 times t plus 1 to the 19th, which you can rewrite. Let's see, it was factor out 9. So it'd be 1/9 times t plus 1. 19th over, to factor out a 10/9 in the denominator. Leave it as a 10 times 9 in the numerator. Or 10 divided by 9 in the numerator. Plus 9/10. So what we should have 19 times t plus 1 to the 19th power all over. Should I do that? Maybe this is what I get for rushing. I would just glance over at my notes. Simpler thing to do would just be pull out a factor of 10. Or 9. It's 9 then. So 9. 1 plus. I'm trying to do too much at once and I'm panicking because I need to get you out of here. How about we just leave it 190/9 times t plus 1 to the 19th over 1 plus 10/9. So if you try and do anything else, apologize, please erase. And then the last thing was we said the question we wanted to answer with this solution was, how many mice do they expect to see in 8 days? So what would I do? I'd plug in 8. Punch it into a calculator and then see what the answer is. I have 190/9 times 8 plus 1 to the 19th power divided by 1 plus 10/9, 8 plus 1 to the 19th power. And now I see what the simplification is. And then if someone has a calculator, you can punch that in. And I don't have the value because I did a slightly different problem than what's in our lecture notes. So anyone got a calculator on? Actually, your calculators might not handle it with a 19. Well, I go type this into, well, actually, I can't do this on my computer without ruining the screen. So I guess it's anticlimactic ending. But I can at least explain what I was trying to do here with the constant, because I see the time. This is a number times a number divided by a number, then divided by something else. So I see A divided by B, then divided by C again. I can just move that 9 down into the denominator. And I just multiplied everything down here by 9. So 1 times a 9 became a 9, and 9 times a 10/9 became a 10. (90 times 9 to the 19 divided by 9 plus 10, 9 to the 18th. Let's see what we get. 18.99999, which means essentially how many mice? 19. So we essentially have 19 mice in the field after 8 days. Go from 10 to 19. Not going to keep talking. If you have any questions, feel free to stick around and ask. It's an important type of model they actually see in a lot of biological sciences called a logistic model. Because with these models, there is a capacity to whatever population you have. But otherwise, enjoy your weekends. I'll see you all on Monday. Yeah, let me do this. It'll be smaller, but you can get a lot more. And oops, hold on, I can do that and make it a little bit bigger. Oh. Yeah, that didn't help. Let's do fit to window. Looks like everyone was able to get everything. Right, good.